Hello, good
Hey,
morning.
Oliver. Yeah, good morning. Good morning. Yeah, okay. Fantastic. All right. So, yeah, we can get started as soon as possible
Okay,
because you have a class at 10 a.m., right? So maybe you
yeah,
can, yeah, we'll try and finish up as soon as possible so you have a lot of time before your class. Okay, all right. So today we can just set up things and see how far we go, and then after the next meeting, you'll probably have a little bit more done. So we'll have more things to discuss and so on and so forth. Okay. So I sent you
okay,
an email this morning. Did you get
okay.
it?
Haven't checked it yet. Let me see.
Okay. And what computer do you have, by the way? Do you have a Mac or a PC?
I'm using Linux.
Linux, great. Okay, fantastic.
Yeah.
All right, all right. Um,
All
are you
right,
running
so
Linux on a PC or a Mac?
it's
Custom built
it's
machine? You?
Linux out of the box. It's from System 76, a Linux manufacturer.
Oh, I see. Wow. So they sell you a Linux PC, a complete Linux PC?
Yeah, they're the creator of the Pop OS, the open
Right. Okay.
source.
Yeah. I
Yeah,
always thought Linux was, hackers will have to install it on their own, but this is
yeah.
cool.
I mean, I've tried installing it on my own, but for laptops, I think
It's a pain.
sometimes there are like, hardware problems. So I ended up just buying a customized
Yeah.
laptop.
Yeah.
Right.
What I used to find was, you can get Linux installed on your own, Fedora, Red Hat, and things like that. But it's just like 3 or 4 hours of work,
Yeah,
just getting all the drivers and getting things to work. And
yeah.
that's what you pay the money for, to get it pre-installed.
Okay. So the folder is called new and I'm in.
Yeah. In fact, why don't you do this? Why don't you share your screen?
Yeah,
Yeah.
definitely.
And then I can see what you're doing, and we can.
Let's see. Desktop. All right. So, all right. Okay. All
Oh,
right.
you got it and you unpacked it? All right, let's go to a command prompt. Before you go into the here, let's go to the command prompt. Yeah. All right, you are in that folder. It's called new, is it?
Yeah.
Oh, yeah, I must have not. All right, just rename the folder to LM experiments. Just cd dot dot and rename the folder to LM experiments. Okay. All right, great. Now, yeah, see CD in there. Now,
Yeah,
let's
I'm
not
in.
go to VS Code. Is this VS Code or
No,
some
this
extra?
is a Vim.
Yeah, yeah. All right, let's not use the GUI. We'll just stick to this. This may be faster.
Uh,
Just change into that directory and do an ls. All right. All right. Now, let's go into the bin directory and take a clean.sh make and grab stats. Okay. All right. Okay. So I remember. I remember everything now. Right, what we did. Okay. So here is the basic problem that we're going to work on,
yeah.
and this problem.
So let me clean
Explain.
up some of stuff first. God, yeah. Um, all right. Okay, go
All
ahead.
right. Yeah, cool. So the basic problem is actually very easy, and you may be able to do it really quickly. And so we'll have a lot of scope for development and expansion of that after you get the basic thing done. So the basic thing is there's a whole bunch of famous authors online. Yeah,
Yeah,
Mark Twain here and all.
yeah,
So now suppose someone tells you, well, you know what? I have my own writing. I want to
mm-hmm.
know whose style my writing is. Is it my own style or does it match Shakespeare or things like that? Okay.
Okay,
So we'll do a very simple project first, just to
mm-hmm.
say, given a random piece of text, you're just going to
Yeah,
classify it as saying, very likely that this was written in Shakespeare style or,
okay,
Charles and so on. So it's very simple, and we'll just use a statistical. So no, I know you mentioned you've been playing with neural nets and TensorFlow and so on, so forth. We'll
yeah,
just do a basic statistical model first, because
okay,
all of these other sophisticated models are also underlying statistical models, which they've
yeah,
gotten so complex that we can't look at the parameters anymore. It doesn't make any sense to us. Yeah,
yeah,
so just do play with basic statistical models, and
mm-hmm.
then we'll and if we have time, we'll slowly develop the model better and better, so that we get to a place where we say, okay, now the number of parameters in this model is so much that the humans can't deal with it anymore. Now we'll start getting an opaque black box model to deal with it, and then you can have all these sophisticated models you can pull off the shelf from Google and Amazon and things like that. Yeah.
Yeah.
So that's how we'll do it. So the idea, basically, here is that we're going to build unigram probabilities for each of these. All right, let me start. So on Gutenberg, do you know there's a site called Gutenberg.org?
I don't know.
Yeah, just open a browser. Go to Gutenberg.org. Gutenberg.org.
I don't know if I spelled it right, but
Gutenberg.
wait, it's not so clear. Probably not.
Actually, just
Oh,
type Project Gutenberg.
no.
Yeah, Project Gutenberg. Yeah, Project Gutenberg is where you want to go. I think it is the first link. Yeah, that's the one. That's the one. It is the same URL that you typed, isn't it? Gutenberg.org.
No, I typed another R, an extra R.
I see.
But yeah. Okay.
All right. Now go to the place where it says find free ebooks. Search and browse, maybe. Search.
So are you gonna do like web scraping
Yes,
first?
and try browsing options. Try browsing options. No, there must be a list of all of the authors, right? Yeah, click English.
Where's English? Here.
And
then authors. Just
oh
click.
wow, they got a lot more now. Yeah,
starting from A
any of
to
them, yeah.
Z.
A.
Right.
Okay, all right. So there's a whole bunch of authors here. Just click on let's pick an author that we know. Okay, I don't know any of these guys. Just scroll down. We'll see if
Maybe go to Mark Twain.
Yeah, no, he'll be under T. Twain. T.
Oh yeah. Let's see.
And it'll be at the very end of this list.
Twain.
There you go, the entire project. All right, so here, that's all of Mark Twain's letters, works. And you'll also find for any author you like, so, and not just English. You can do this for Chinese, for, any language we select. We can say, all right, let's go and find out. Most probably, well, I shouldn't say most probably, okay? Because, other than English, in other languages, there's so many authors, and Project Gutenberg doesn't even know. It's really an English website, so they probably just sample like the top 5%, or 2% of those authors. But English, you have a pretty good selection, I think.
Yeah.
So the idea is that click on one of those. Yeah, all right, just click on one of those.
Okay, wait a second. This Zoom stuff is blocking it. Oh, did it just stop sharing? Okay.
Yeah.
All right. Here.
Yeah, let's try further up. E-text. Do you have e? Can do plain text. Plain text. UTF-8. Okay, I think.
Oh yeah.
Great. Okay, so if you scroll down, you'll see it says at the top is all header. Okay, this is all Gutenberg information saying, oh, I got this, and so on and so forth. Somewhere down there, you'll see some lines, and then the actual text. Yeah. All right. Yeah. So the actual text starts somewhere below. Now, for each one of Mark Twain's works, you'll find a file like this.
Okay.
Now, the challenge here is to say, if you are an AI system, and I've given you lots and lots of works by Mark Twain, by Shakespeare, by Charles Dickens, right? And all these people, and you've read them all. Now, in your mind, you have a model. After a while of working with C++, someone shows you a random program, you'll say, hey, that's C++, yes?
Yeah.
Even without looking at the details of it. So like that, when people read these authors, they tend to develop a model of their style. And that style is in our head. And that means that if you get a random piece of text that you don't know who was written, which means you have never seen that text before, it's not part of your model.
Yeah.
Can you tell with some degree of certainty, not 100%, well, this is that author. Okay, that is the basic problem we're doing. It's a very fundamental machine learning problem, just text classification.
Okay.
Now, so we'll do that. Now, this project that you do, eventually, if we have time, can be turned around. Instead of saying, give me some text and I'll tell you who wrote it, you can actually turn it around. It's a very simple thing, right? And say, rather than saying, give me some text, I'll tell you who wrote it, you can say, give me an author, and I'll give you some text that resembles the style of the author. Okay, so if you have an English class and they say, oh, write me something in Shakespeare style, you can just go to your program and say, give me 100 words in Shakespeare style. And of course, it's not going to be as good as ChatGPT, right? Because ChatGPT it's a much bigger model. It has many machines in working in parallel and so on, so you can generate much, and it has more evidence than what we're going to use. So but you'll get an idea at the end of this project. You already have an idea how to build something like a ChatGPT, right? How you can build generative text machines rather than classifying text machines, because underlying implementation it's basically the same. Right. So, so the way we're going to do this is actually, a CS 101 way. It's very, very simple. All we're going to do is just going to rely on word frequencies. Okay, word frequencies. So, and what we'll do, and the hypothesis here is that authors, no matter how prolific they are, they have somehow in their minds, and they have subtle subconscious preferences for certain words and certain word constructs. In fact, they also have preferences for certain word sequences and some phrases, right? Some phrases, how many times they use a question mark, an exclamation mark, right? Say lots of exclamation marks, you already know it's a teenage author, right? So like that, so all of these things can be leveraged. But we'll do very, very simple right now. And what we'll do is basically say, we're going to scan the text of all of the authors, and then build unigram probabilities, meaning we're going to build the probability that a particular word was written by an author. So for example, Shakespeare might have used indignation many times, right? Whereas Charles Dickens uses anger instead of indignation. Many times. So the probability of indignation, if you see the word indignation many times, that subtly raises the probability that it was written by Shakespeare compared to Charles Dickens. Well, of course, that is not the only thing. There'll be lots and lots of words. So what we want to do essentially is calculate what is called the perplexity of some given piece of text. Which perplexity is nothing, it sounds like a complex word. It is really the average geometric mean, right? So not the average probability of a word given a particular author. That's what we're going to do. Yeah. And so now you don't have to take notes like this, because this is being recorded. You can watch the recording later.
But it's just easier.
Yeah. All right. Sure. No problem. Okay. So what we can do is right before we go into we want to go into some Google Doc or something where we can share the document. So we'll have a little bit of math to work through. Yeah, we'll work through a little bit of math. I think I'm pretty sure you'll be comfortable with that. Yeah. Very little of math and stats. I'll walk you through the whole thing, and then that model is what we'll be implementing in the code later on. So, but before we do that, let's take a look at that text. Go back to the browser screen where you had the text. Okay, so you see here that the text is presented in a way on the site, which is kind of easy for us to see because we can read it, but still there's a lot of junk in here. Okay, so if you go to the top, you have all the header information that needs to be taken out. Yeah, all of that needs to go, and then even within the paragraphs, you have paragraphs, but within the paragraphs there are many sentences. Right, so each sentence ends with a period or an exclamation mark or something like that. Yeah. Okay. So what we want to do is we'll do the first pass is going to be just cleaning up the text. Okay. And for cleaning up the text, we don't want to use C++. And that is the purpose of that cleanup.sh script that you had before. Right. So if you had a script called cleanup.sh, now that is a very basic, totally basic script that is meant to give you an idea of how these things go. So in fact, if you control, can get out of the in your in the terminal, you do a less. No, which directory are you in? Which directory are you in?
I'm in the bin.
Bin. Right. So go back one level. Right. Now do thank you. Right. So do less space data/authors. And tab. Yeah, okay, great. let's pick Shakespeare, maybe. I don't know, pick anyone. Okay. All right. So if you go further down, you'll see all of the Shakespeare. Not all. This is just one. I think this is just one of those, right? And further down, you'll see. All right. So what we want to do is clean this up so that the output, which is what we get from here, is basically a stream of text. We'll call that a stream of tokens. Okay. We'll call that a stream. And when I say tokens, I basically just mean a word. Most of the time it's word, right? Further down the line, when your model becomes more sophisticated, your tokens may become other than words. Your tokens may become semicolons, you know, all these things. But right now we're just going to say words, all right? So these words, we want to break up, we want to clean up the text, get just like the C preprocessor does, right? So it gets rid of all the comments, right? And you know, the code is could be formatted differently. It cleans it up and brings you one token at a time. That's what the C preprocessor does. So we're going to do exactly the same thing to this. And it needs to go through this big file, toss all of the header comments and all these things. And then it's going to take each paragraph, and it's going to break each paragraph into sentences, one sentence on a line, so that each sentence is on a line by itself. And after that, it's going to do some normalization of the text. Right? Normalization meaning I'm going to change everything to something that is predictable, I know, that I can handle. And the normalization usually takes many forms. And again, normalization is also a process of simplifying the text, meaning there's evidence in here that I can't handle, so I'm going to get rid of the evidence. Because the whole text has all of the evidence. It actually even has, this was written by Shakespeare at the very top, yes? So all of that's evidence for a system, but we're going to get rid of it because we don't want to model it, because for various reasons. Modeling is difficult, or it could cheat the system and saying, you know, it could inject bad information in there. So we're going to get rid of all this. That's called cleaning up the text. But in addition to that, we're also going to say we're going to change all of that to the same case, not uppercase and downcase, you know, lowercase, all of them in the same case, right? And then we're going to break it up so that it's one sentence on each. Oh, we covered that already, all in the same case. And then you can also do more pre-processing as you see fit, saying, well, you know what, I'm going to inject another method at the end after all of that has been cleaned up. I want to change things like st dot to street or saint. You don't know where it is, right? Saint Francis Street, st Francis, st full stop, right? So there you can make heuristic decisions and say, well, you know what, if there's an st at the end of a sentence, it's a street. If it's before a word, it's a saint. But during the initial stages of a project, we should really not trouble our minds with that level of detail. We're going to say, until we get the whole pipeline working, we're simply going to say that all the st dot becomes saint, or all the st dot becomes street. You know, all the dr dot becomes droid or doctor, things like that. Yeah, mr dot becomes Mr. So you perform all that cleanup too. Now, this script here doesn't do all of that. It just does some very basic cleanup. So let's run that script and see what we get. Okay, so in your terminal, type cat. Cat. Oh yeah, cleanup.sh. You can type cleanup.cleanup.sh, and then data/authors. Oh, you're in the bin directory now. Okay. Shakespeare. Okay.
We're just gonna output
anything you want. Charles Babbage. All right. I don't know. Right. So let's just do a less. Pipe that to less. Yeah. All right. Can you increase the size of this thing here so you can? No, not that. You can the right side. You have this terminal. Yeah. All right. So here you see a bunch of things have happened. Okay. So it has taken that text and it's cleaned it up so that you have one sentence on each line. Remember, I'm doing this using SAD and some basic Linux stuff, so it's not as sophisticated. So you may see some errors in the cleanup also, like some sentences may be broken in half. And that's okay for now. Okay, you can always come back when you got the whole thing working. You can come back and do more sophisticated cleanup, and you can get it cleaner and cleaner and cleaner as much as you have time. Yeah. Okay. So now you see a few things here. The sentences, one sentence per line. Number one. Okay, and then the beginning of each sentence has a meta tag. That's S within angle brackets. That says this sentence is starting here. Okay. Likewise, at the end of the sentence, you have /s, a closing sentence tag. Now those have semantic value for us. That's why we are injecting those, right? Semantic value, meaning that it's important to know the very first word that the author uses, because the authors have preferences for the first word they use in sentences, and
Oh,
authors also have preferences for how they end a sentence.
okay.
Yeah. So we have these markers on both sides, because that's
Yeah.
also going to be part of our model.
Yeah.
So, and these models and these markers was also, each token now will have a probability, right? Each token will have a probability of occurring in a text, and the probability we will just, is a unigram. So unigram meaning it is just a raw probability, independent of the context, right? So if I say a bear, a man or the man, okay?
Yeah.
And so the man in the story could have a different probability if it is following the word the or if it's following the word a. Yes.
Yeah.
However, if it has very low probability following the word an, right? Nobody says an man, right? Because they say a man or the man, but they don't say an man, right? So they say an apple, but they don't say a apple. Yeah.
Yeah.
Right.
Yeah.
So the probabilities of words depend a whole lot on the probability of what came before the word.
Yes.
Yeah. All right. Good. All right. I'm glad you're saying yes here and all. So that means that there's a whole lot more information you can get by incorporating the history of words.
Yeah.
Right. In calculating the probability, these are the conditional probabilities. What is the
Yeah.
probability of A given that B occurred before?
Mm-hmm.
Yeah. We were not going to do that in the first pass. The first pass is just going to be unigram, meaning we're deliberately using less information than given to us. In fact, a whole lot of information has been, because the context is being ignored, we're just going to say unigram probability. Unigram meaning 1 gram. Okay. So each word has a probability of its own. And we're going to simplify and say that we'll even assume that the probability is just going to be approximated by the relative frequency of the word in a corpus. Meaning that if man occurred 53 times in a corpus that has 1,000 words.
Yeah.
Right? The probability of the word man, the probability of the word man is 1 over 53 over 1,000 is 0.053.
Yeah.
Yeah. So we're just going to ascribe numbers to each of those words based on the probability that of the word in the corpus. Later on, after we've got this working, what we'll do is we'll also develop a bigram model. Bigram model is what's the probability of the word given its history. Yeah. And eventually you can get this more and more sophisticated, so that you can have history of not just one word, you can have a history of more words. So if you have lots and lots of huge computing resources, like you have an entire data server farm, right? Farm in Iowa, Antarctica is running hundreds of computers, thousands of computers, and you have lots and lots of data too. You have lots and lots of data, meaning you have millions of words, right? The entire collection of the Wikipedia or something like that. Yeah. Then you can say, my language model can be so sophisticated that it can use the entire context all the way from the beginning of the sentence. Right.
Yeah.
And so we won't do that right now. And you can throw in other evidence also as time goes. So we'll just do unigram first and then develop the bigram, maybe to trigram later on, and you'll see how the accuracy of prediction improves each time you input more and more context. Okay. So so this is what we want to do. Now let's go to that script that I had. I'll just go very briefly describe what the script does.
All right.
My phone. Give me 1 sec, okay? Let me get my iPad and phone. Not that I need it right now, but
okay.
Just in case. Okay. Great. Okay. All right. So here, are you familiar with these commands like sed and tr and things like that on Unix?
I'm only not familiar with tr, but others I've been using like awk, grep,
Oh,
sed.
great. You've been using awk, and you are familiar with tr, you're saying?
I'm not familiar with tr.
Oh, so you know about sed and all, sed and regular expression.
I know about sed, regular expression.
Oh, fantastic.
And grep
okay.
and awk.
All right. So I have a feeling that we'd probably be able to take this project all the way to generative text also, because you already coming in with all this background.
Maybe we can build an app for that.
Yeah. And if you're interested, I can even show you how to build a web app. Have you built you've built web apps before, right?
Yeah, I've been building a lot of web apps.
Yeah. So I can show you how to develop a web app in an Amazon bucket, or no, it won't be a bucket. You need a server because you'll be doing some C++ crunching also, or Python crunching. But we can get a server. It's very cheap, like $1 a month or something like that. That you can host. You can get a domain, oliverchoi.com or something like that. I don't know. That's probably gone, but you can find another domain. And I'll show you how you can create an app which will say, do you want to generate sentences or do you want to classify? And people can go, random people on the world can go and type something in and say, hey, you are like Shakespeare, you're like Charles Dickens. Okay. And that would be a fun app. I can show you how to do that. And it's very straightforward. So here, all I'm doing is that this is really a hack. Okay. You can clean this up in Python later on. You said Python, right?
Yeah.
All right. So initially you can use this. And what you can do to figure out after, I'm just going to do an overview of the script because I'm pretty sure you can figure out what this does. Because all you needed to figure out is that you go into the script, comment out everything except the very first set command. So everything from tr A to Z is gone, right? So you comment out everything. And then run it, and then you'll see the output and say, hey, that's what's going on if I only have the first thing. And then take the output of the first thing and send it to the TR. You'll see, oh yeah, okay, the previous thing now got all turned into lowercase. And then take the output of the TR and send it to the second, second TR. Oh yeah, okay, it's the same thing, but it's deleted all the double quotes. TR-D. No, TR. You said you didn't know about TR. TR is basically a command called transliterate, right? I think it's called transliterate. And basically all it does is that it replaces characters one for one. Okay. So if you say TRA-B, it'll replace all A's with B. That's all. And you can
this part is just to delete to lowercase to all the characters. Okay.
Yeah. And the only condition for TR is that the two parameters you give it, A to Z and A to Z, they should have the same number of characters in the range, right? A to Z goes to A to Z. So each character will be mapped correspondingly.
And this means to delete all the things looking like this.
And then here, delete, I think in delete, within square brackets, you can give it a regular expression. No, within square brackets, you can give a regular expression, but within square brackets, you can specify all the characters you want to delete. So it's a disjunction. You can say delete all of the characters, any character between the square brackets, you delete.
Okay.
Yeah, so that's what it does. And then, so here the other thing I'm doing is that I'm taking all the commas. The third set line is I'm taking all the commas and making sure the space is on both sides of the comma, not just one space.
Okay.
Yeah, but that will also introduce an extra comma sometimes because, your comma may already have a space. Now it'll have two spaces. Yeah.
Yeah.
After. So now then I compensate for that by taking, let me now condense all multiple spaces to a single space. There's another regular expression somewhere in there, right? I do that. And the way again, it's a very hacky way to split up sentences on different lines is every period, every full stop, what I do is there's multiple lines there. What I do is here's what I do. I think replace all the. I think I replace all the new lines. Yeah, I replace all the /n new line characters with some special character, maybe tilde or something. So now everything is one thing. And after that, I replace all the periods, the full stop with dot and new line now. So now everything that ends in a dot will come on a line by itself. And then I go and reverse that. I don't know. I do a bunch of things there. Okay. But I can, if you are unsure about anything that happens here, you just have a Zoom call or an email. I can clarify what's going on. But I think you won't have to because you'll probably be able to see what's going on and figure it out and probably come up with much better way of doing this using a Python script. Because in a Python script, you can basically read in a line and then send it to the first function that will downcase it, send it to the second function that will remove, split it up into different sentences and so on. So you just call one module after another. You can comment out these modules and see the effect. But the end effect is that your cleanup.py script or whatever it is that you write, you can reuse it. You don't have to write one now. You can use this for until you get to, a place where you're ready. Output of that script is basically got to be something that is clean, like what you saw coming out of the script. Yeah. Now, what you saw coming out of the script is clean, but it does discard a lot of things, right? It discards a lot of information. But eventually you can say, well, you know, I don't want to discard so much information. In fact, what it does is, if you go to the script here, you see that, on the third line from the bottom, set -e, it just deletes, I think it deletes, it deletes all non-printable characters, meaning, you know, in the script, even though it's all ASCII, there are some characters that are non-printable, you'll see, right? If you do it, if you do a cat-v, you'll see the file, and there's non-printable characters here and there. I don't know how they got in the file, but they're there. So it deletes those characters, and it also deletes some other stuff, which you may say, well, you know what, that's being deleted. It actually has information. I don't want to delete it. I want to turn that into a token. You can do all that, okay, in Python. And so, but the end should just be, you know, sentences, tagged, 2 tags, 1 whole sentence, 2 tags, 1 whole sentence, lots of those.
Yeah.
Now, once you get this, it is now very, very simple. Now let's try this, okay? Let's try this. Now, go to the command prompt, up arrow to get what you had before. I know, you can do an up arrow, get what you had before, the command that you had before to do the whole thing. That one, right? Now don't do less, don't pipe to less, but instead we'll do something, okay?
Save it.
Oh, actually, I got to see the output to figure out what to do. Right, so type less again. I want to see what we have. Yeah. So we want to break it on the space so that we get 1 on each line, and then we can do a sort dash here. Oh, all right. Okay, good. All right. So now, Q out of this. All right, up arrow. Up arrow. Now instead of less, let's type tr. Let's transliterate. Now here's what we're going to do, right? We're going to substitute all the spaces with a new line character. Okay, spaces with a new line. So type that. I don't know if that'll work, but try that. I want to see if it worked, right? Pipe. No. Oh, it didn't work. Okay, right. So do space within single quotes instead of, but /n will work strangely. All right. But you got to do two backslashes, not 1 backslash, because if you have 1 backslash, the shell will get the first one.
Okay.
Yeah. Okay. So there you go. All right. So now each word is on a line by itself. Yes. All right. Now, how do we find the count of all these words? How do we count all these words? How do we know how many times in occurs in that corpus? How many times any occurs in that corpus?
Building a hash map.
It's the easier way to do that on the shell. Yeah, absolutely. That's what we have to do. Eventually, when you get it to a C++, when you build a hash map, you'll do it with a hash map. But since we're trying to figure it out here and do some, quick checks, we'll do it on the command line. Okay, so up arrow 1 more time. All right, now pipe that to sort, and do a less of that. Right, there you go. All right, now you can pipe page down. It's been sorted. Page, keep page. Yeah, there you go. Eventually, you'll start seeing your words.
I can just search.
There you go. It's already started. I don't think you'll have any more. You can keep going. So I see A, the letter, the word A occurs so many times. That's why you have so many of those, right? Now here, let's do one more thing now. So now that we have, Q out of this, up arrow. Now it's been sorted, up arrow. Now, instead of less now, let's do unique space -c, okay? Unique space -c. What that does is, unique, UNIQ. Have you used that command before?
Yeah, I've seen the technique of using sort and then unique -c.
Yeah, it's very common, very common. Yeah. So what this does is, if it's already in a sorted stream, unique will basically just collapse all the consecutive runs into a single one and put a number in front of it saying that's how many. There you go. Okay. So now it's counted everything, and these are all the counts of all of the words. Cool. Now we want the counts, but if you look at the top, you still see a lot of junk. Yes, if you go right to the top, less than sign will take you to the top. Yeah, right. So see, there's still a lot of junk. So and we don't want to model these guys. Again, you see those numbers? You see those numbers in your Python script? You'll probably have a module that says convert numbers to words. So instead of 1000, you may say ONE space THOUSAND. Yeah. So eventually, not now, right? For now, we're just going to throw it away. We're going to say all these other evidences we're just going to discard, because we want to keep our project simple. Yeah. So was I doing? Yeah. All right. So these are the number of times these things have occurred. So what we want to do is just say let me just look at the most frequent words, because the chances are any author they'll use words that are very unlikely in their own vocabulary. We can say safely we ignore those words.
Sort again.
Right? Sort-nr, sort-nr. No, sort-nr means nr meaning sort numerically, and now present the results in reverse order, so the highest number is on the top. Yeah. There you go. Okay. So this says in this corpus, a comma occurred 5,400 times, right?
Yeah.
And then there are 3,300 sentences, 3,351 sentences, because each sentence starts with this and ends with that. So you can see that, right?
Yeah.
And then the word "the" is the most frequent. It occurred 3,200 times.
Yeah.
This is crazy, isn't it? Which means that every sentence has at least one "the" in it. And that's telling about the author. It's some author, right? And so on and so forth. Now, if you go to the bottom, scroll down. Oh, you went all the way to the bottom? No, don't go all the way to the bottom.
Right.
A few pages down. You'll see that. Yes, you'll start.
Let me do again.
Yeah. Right. You'll see some junk starting to appear. All right. So further down, but you'll see, fortunately, the junk is low probability, meaning the junk is not that frequent. Yeah.
Yeah.
So now that means we can do something cool.
Yeah.
We can say that we just want to deal with the vocabulary of this author, not all the junk. Right. So the junk creeps in. We want to discard all the junk. So what we can do is essentially just build a vocabulary of this author, and meaning that we'll just take the top and most frequent words, and that is the vocabulary of this author. Everything below that, we're just going to ignore. And typically what people do is they'll look at this. They'll look at this, page down, all the way until they get to some obvious junk, and say, okay, that count, right? Everything below this count is gone. So that's how they do it. Now, however, what we want to do is our vocabulary should not be, the vocabulary of this project should not be restricted to the vocabulary of one author. Okay, the vocabulary is going to be any word that we can see from all of the corpora, all of the, Shakespeare, Dickens, Mark Twain, all of them thrown together, get all of the words used by all of the authors, do exactly what we did, count, reverse sort and everything. Now we see the junk at the end, and we say, okay, now all of the words occurring below some threshold, we're going to discard. Now, all of the words above that threshold, that is part of your vocabulary.
Yeah.
Right. And those are the only words which we will respect in any of the author's text from then on. Right. So meaning that if a word is not part of the vocabulary, we're just going to ignore it for the basic model.
When you say threshold, do you mean like the word frequency?
Yes, exactly. You can set the threshold to that is for determining the vocabulary, right? So in fact, what you can do is, right. So Q out of this, now you can say instead of cat, just cat. No, right. I see. All right. So get rid of everything from /data to Charles Babbage, right? Get rid of that part.
I mean, only start with sort.sh.
And we want to, all right. So let's pipe, go to the beginning of the line. Beginning of the command line. So cat /authors star.txt. Star, all of them. What is in test.txt? I want to see what is test. What is in test.txt? I wonder if that was put in there. Nothing in there. Just remove the file.
We are testing.
Get rid of the file. Delete it or end the file.
I can leave it and delete it later.
No, you just get rid of it now, because that was a file that Nathan
left. It's gonna mess up with our comments. A second.
Right. Gone. Right. So now you can do star.txt and pipe it through the same thing that we had before. No, you need that's right. You need to pipe it to clean.sh, and then you can do and you need to do a sort unique sort. Oh, no, yeah, you need a TR to change the TR to change the spaces into, yeah, new line. Yeah. All right. So this is from all. Something funny here. It's only got the first one. It looks like it's
I
only got the first one. Yes.
think it's a problem with the clean.sh
Yeah. Okay. But
because it
I'm not going
doesn't
to go. I'm
accept.
not going to debug it. I'm pretty sure you can debug it. Yeah.
Yeah,
If you want me to debug
I
it now, I
think
can debug it
we
with
have
you.
to like, yeah, so this is supposed to like concatenate everything together, right?
Yeah, it's supposed to concatenate everything, and clean.sh is just getting its input on standard input. Yeah. So it should
Yeah,
get
it's a
everything.
little bit weird.
Why is it not getting?
Right.
Maybe the other ones are empty. Do an ls-l of the author's directory.
Mm.
ls-l. Oh no, they have stuff in there. No,
Mm.
just do Shakespeare alone. Maybe we'll see if we get different numbers.
Okay.
Oh, this is funny. It's doing the same thing for everything. Maybe inside of clean.sh you got something. Inside of
Yeah, maybe
clean.sh.
the file is like, yeah, it's
Oh
using the
yeah, yeah,
same
yeah.
file.
Okay, all right. So no, that should not be that. So change that to. Oh yeah, that was for debug. You can comment out that line. You can comment out that line. Comment out that line. Yeah, that's what we need. Yeah, okay. No, you can have the comment after. Yeah,
A
okay.
comment. Which
Hang
one?
on. You can have that comment after the pipe symbol, because then it'll,
Oh,
because the slash at the end is also commented out.
can I do
There you go. I
that?
think that'll work.
Oh.
No, you still I think you're missing a backslash. The first one.
It's
Uh,
just not displaying here.
no,
It's
put put
just,
a put a backslash there. Put a backslash there. No pipe symbol, just a backslash.
oh,
Space backslash would be nice. Yeah, yeah. Now, do you have a pipe symbol in front of the sed?
said no.
The first sed. There you go.
No, because right now the pipe symbol is, uh, it's formatted by my text editor.
No, I
So
mean on line number
7. Yeah,
Yeah, there you go. That's what I meant. Yeah. Why is it?
yeah,
Why?
yeah.
Hang on.
It auto formatted it already
Oh, that's
because
very funny.
my text editor thinks that having a slash at the end and then a pipe at the beginning is not
It's
better
better.
than having. It thinks that having the pipe at the end is cleaner. That's why it formatted it. Because
Oh, I see. Okay.
I'm using some formatter.
Okay. All right. That's fine. As long as it's syntactically correct, it's okay. It's not just not what I'm used to. Right. So you have
Okay.
a. So is it okay now? Is a pipeline? I can't read because the colors are all different. But is it okay? Does it look right to me? To you?
Yeah, we can see if it works. I think it's good. Yeah. Let me
Yeah. But
do.
do a less there. Yeah. No, it
Wait,
didn't work.
didn't work.
Get rid of the less and get rid of the
Uh,
less and run it.
no, the problem is with the.
Oh,
Oh
where
no,
is where is the error? Where is the error? What error does it give you?
cat
Just
no
run the
such
command
file.
itself.
It
Oh, it says
says
that's the command.
syntax
That's the error.
error. Yeah,
Yeah. Okay. So
line number
get
7.
back to
Yeah,
this.
that was what they were
Which
saying.
what editor is this? What editor is this, by the way?
NeoVim.
I see. Can you just use Emacs or VI Vim or something like that, which doesn't do your reformatting? Do you
Yeah.
know Emacs? Do you know have you used Emacs?
No, I'm more of a Vim user.
No, VI. You've used VI. This is NeoVim, right?
Yeah,
So just use VI clean dot.
yeah,
Okay. Oh,
right.
it's already changed everything. We want the backslashes at the end and then all the pipe symbols lined
I
up like
can
this.
pull a file again.
Yeah, yeah, yeah.
Can
Is it
pull a
possible
file.
for you to do that?
Yeah, let me see.
even this has been reformatted. How come this is also reformatted? Oh, this is the old one. Is this
No,
the old one?
I haven't opened this is the old one. I haven't updated it. Wait a second. Right.
Okay, now this is updated, right?
I think this should work, right?
Okay, now this I think should give you, yeah, do Shakespeare. Nothing?
Wait.
Do something
Script.
else. Do something else for now. Not Shakespeare. Do another author.
I think
Oh,
there's something wrong with this.
okay, that's all right. So,
Is it because of this?
oh, wait a sec. No, run the command. Run the command you had before, except get rid of all that tr and all that other stuff. Just clean.sh only. Just clean.sh.
Oh,
After clean.sh, get rid of everything. Yeah. Nothing? Okay, good. So, but yet the previous thing worked, right? The previous thing.
yeah, this line works. So
That is funny.
this is not passing the right file as a parameter.
No, one sec. Okay. Why? It should just cat because that dollar star should
Wait, shouldn't
expand
it
to
be
blank.
like $0?
No, not star zero. It's not the first parameter. You want everything in there. Is if nothing was given, that should be blank. Meaning, get rid of all of that. Just have cat. Just have cat. Only
So
cat, no
just cat.
parameters. Right? Yeah. Now, obviously, if you run the command now, save it and run it, it should pipe your bell Kendrick or whatever it is into this guy, right? Because cat is basically just taking the input and sending it to the output. Why is nothing happening there?
No, I canceled it. So I think we can just run clean.sh against this file, right?
No, right now it won't work because cat doesn't have any parameters.
Oh,
I'm no,
yeah.
it used to it worked. Hang on. Yeah, run.
Mhm.
Yeah, pipe that to clean.sh and do a less, or just do a head. Yeah, just do a head. Pipe that to head. Yeah, right.
No, nothing.
Nothing, right?
No output because
No output.
I think
So
this
go back to your
output of this is not passing to here.
yeah. So go back to your script again. Go back to your script and put that thing there. Put the Charles Babbage thing in there after cat. Put the Charles Babbage thing after the cat.
This one.
Yeah.
Do you have for
No,
me?
I was thinking, the same as the previous, dot slash author slash Charles Babbage dot txt.
Oh, okay. Right. Let me think.
Yeah, we can just use the previous one.
Yeah.
Yeah. So, yeah, do that.
So we're not gonna cat that,
This works, but it doesn't work for Charles Babbage. Yeah.
but it's not considering this at all. It's just starting from here.
Okay. So I think I have a theory why it may be, but I'm pretty sure you can debug it. I'm not going to debug it here. I have a theory. So in my sed, if you go back to that script, in that in the line of sed, open the script.
Yeah.
Right. So you see how I delete all the lines from line number 1 to a line that has the word start of the project.
Okay.
All of the lines from the beginning to that is deleted, and I only take everything below that.
Yeah.
Now, my hypothesis is that it never encountered that line, so it deleted everything. In Shakespeare.txt, it never encountered start of project. That's my hypothesis, right? I don't know. Let's not debug it here because we can develop the math model and so on. We can come back to this obviously later on to debug it. But I can see you have a puzzled look, so you're obviously going to get to the bottom of this and fix it
I think
yourself.
the problem is maybe like the parameter is not passed correctly, but I'm not sure.
Which number is not correct?
The parameter, the cat output is not passed correctly to
Oh, you think that's what it is?
this shell script. Yeah. because before we can do like cat a
Yeah,
file
just
and
do
then
cat
do the
before.
rest of it. But I
Oh,
think
let's there's one thing
I
we
think
didn't do.
we can just remove the first line.
Yeah, remove the first line.
Just
Yeah,
remove the
remove that
first
line.
line.
Put the cat one thing back. Put the cat thing back. Put the cat. Put the cat thing back. You know the other cat. The other cat. The other cat. That one. Yeah. And that line needs to go above the first cat because it won't.
Yeah.
You can't have a comment there. Okay. Now hang on 1 sec. Okay. 1 sec. Cat. Oh, put a blank line after the. Maybe that's what's going on. Okay.
I think
Okay,
what we
yeah.
can do is
Maybe that's
just
what's
to
going
remove
on.
this.
Yeah. No. Yeah. I know what's going on. Oh my
Okay.
gosh. Yeah, I think it's crazy. But yeah, hit enter. Hit enter.
Enter.
No,
And
not there.
then
Not there. Before the cat. Yeah, hit enter. Okay. I think that's what's going on. Okay, because you had a backslash at the end of the comment.
okay.
It said okay. Everything following it is also a comment because that new line got in. That is my hypothesis. Okay. Now try that. Try this. Maybe this will work. Okay. Try this. It'll work. Hopefully.
Okay. Wait, are we?
You try anything. Yeah. Cat. Yeah. Try that. Still nothing.
No. I think maybe we can just remove the cat and then remove a pipe. Maybe it will work. No.
No. Don't do Charles Babbage. Do what is that? Bell Kendrick. Whatever you had up there. Yeah. Control Z out of this again, and do up arrow, and change the Charles Babbage to Bell Kendrick. Yeah, because we knew this worked, right? Okay, all right. So it works for this author, but doesn't work for Charles Babbage. So it's not in the script. The bug is in the data, right? So Charles Babbage probably doesn't have the thing that start of project line or something like that.
Yeah, let's see
Anyway,
what's clean here now. Yeah, so I removed also the pound sign here.
you can put the cat back now. Yeah, you can put the cat back because that is supposed to work.
But this one is working now. Because I think we only need to cat the first time, and then we can just do the rest of the text processing.
Yeah, exactly. Yeah, but the thing is, oh, I see. You're saying you can actually do this on the command lines and cat star.
Yeah.
Try that cat star. But even then, I think what's going on is that it'll only do that Bell Kendrick, and everything else is probably oh no, actually you can't do that. Hey, no, you can't do that. Unfortunately, you can't do that. Yeah, you can't do that. You can't do what? Because when you cat everything together, you see in that script we have delete everything to that start of that sentinel. We'll call that sentinel. Delete everything to the sentinel. But now it's combined everything. You have sentinels in between files in the stream.
Oh, okay.
Yeah, it's a mess. So I think what we need to do is you can figure it out later. I think you'll probably be able to do a much do it in Python, okay? Do it in Python, okay? I think you'll have a much better, easier time doing it in Python. But you know what we're shooting for? At the end, we just need this clean script, clean stream. Yeah.
Yeah.
So I'll leave that that part there. So you're going to be doing that in Python. Make a note maybe in your thing. So you got to do the cleanup in Python. So out there, and then what we want to do is get the vocabulary. Yeah. So now let's do the vocabulary. Let's do the vocabulary. We'll do the vocabulary. The vocabulary needs to come from all of the authors. So when you do it in Python, eventually, you're going to feed all of the training, all of the data you have into your cleanup. And from that, you're going to do the sorting and counting and find the vocabulary from all of the authors. The vocabulary should not be restricted to one author. The vocabulary is all the words used by all of the authors. Yeah. Okay. So that will generate a file, and that should generate one file, 1 word per line, 1 word per line, and maybe in alphabetical order. Doesn't really matter. 1 word per line. The vocabulary should be a list of all possible words the system can ever encounter. 1 word per line.
Like a dictionary file.
Exactly like a dictionary file, like the Unix dictionary file. Yeah. Okay. So all right. So that's what you got to do. You made a note in your notes. You don't have to. But you got to create list. Yeah. Dictionary. Okay, good. So we're going to use that later on. And we call that vocab.txt. Call that vocab.txt. Right? We'll use this later on. Okay, now let's go and develop the math model. So if you can open a Google Doc or something, we'll go to open a Google Doc, and then we'll go to equation mode or something.
Wait a second.
Unless you have, if you have an iPad and you can do it, draw with a pencil, that's okay. But I think, equation mode on Google Docs probably should be sufficient.
Okay. Maybe we can use something else too. We're trying to do a diagram here.
No, just math equations.
Oh, math equations. Right. Then Google Doc, yeah. Okay. I need a
Okay. And you can say here. But let's just start out by typing some text here. So say we want to calculate. Calculate P, capital P, and square open parentheses. This is probability, right? Or you can say probability. P-R-O-B, prob, right? Prob, yeah. And within parentheses, you want to say author, probability of author, vertical bar, given text. Or you just say text. That's a conditional probability of the author given the text. Conditional probability of the author.
Okay.
Yeah. Right. So now on the next line, let's say we're going to say A for author and T for text. Yeah. And also, in fact, what we'll do is the text will represent the text as W1, W2, W3, W4, and so on up to WN. Okay. Each one of those W's is a word. So say let's consider so type this, okay? So say let the text be made up of a sequence of words W1, W2, ... WN. Yeah, W1. Yeah,
I start with that 0.
Doesn't matter. We're C++ programmers, so we should start at 0. All right. All right. So all right. So those are the words. And so what we want to do is we want to on the next line we want to say here let's try math mode here. Okay. So format. I think it's under a format. Okay. Under format. Okay. I think there is math mode. Oh, insert equation. Insert. Not format. Equation.
Oh yeah.
Okay. All right. I can read it, but maybe we'll increase the font later on. Okay. So here we want to say P square bracket P open parentheses uppercase P. We'll just say for probability P open parentheses. So we want to say A given T. Yeah. What's that? Say go to the beginning of the line and say let P of A given T be the above probability. Let P of A given T be the above probability.
About.
Be the above probability. Above. Yeah? Be the required probability. Okay. So here's where we want to right. That means we want to calculate. On the next line. We want. Okay, now you can go to equation mode. On the next line, you can say want to go to equation mode. Yeah. There you go. Right. So say /argmax. We'll see. No, backslash. I don't know if Google understands that, but we'll see. And space after that. Argmax. Space. Oh, it didn't pick up. All right, don't say slash. Just say argmax. Okay, just say argmax. No slash. Argmax.
Argmax.
Yeah, argmax underscore, and say a little lowercase a.
The underscore became something like this.
Yeah. That's underscore makes it subscript.
Okay, cool.
That's good, right? A now and then space, and say /in.
In.
No, IN.
Yeah, IN, right.
IN space. IN space.
Yeah.
Did it turn into? I can't read the font. Yeah, we can do a Command A and you change the font size to I don't know, maybe 15.
Okay.
Yeah, Command A 15. 14. Yeah, 14 is good. Yeah, I think that's A belongs to set of all authors, right? You can say set of all authors. A belongs to set of all authors. Yeah. I put a space before the set. Put a space before the set. Okay, right now. At the end, you want to say space. Put a space. Right. P of T given A. No, this time it's a lowercase a, right? It's P of text given lowercase a
for
times
each author.
No, yeah. I'll explain this very quickly, right? So P of T given A times the prior probability of the author. Times the prior probability of the author. No, times P of A. This is the prior probability of the author is usually just said P of A. P of A, right? Uppercase P of A. Have you got uppercase P of A there? Yeah. Okay. Right. Yeah. Exactly. Now, do you know? Are you familiar with Bayesian statistics? How you calculate conditional probabilities?
I know conditional probabilities, but it was like a while ago.
Yeah. All right. I'll do a hit a couple of enters. Hit a couple of enters. Right. So suppose you have three. Suppose you have. Let's see. Right. So type this out, and then I'll explain it. Right. P of A given B. No, it's a no. All right. P of A given data. Right. P of A given data. P of A given data equals P of data given A times P of A. The whole thing divided by P of data. Right. In fact, let's do it in math mode. I think it'll be easier. We'll do it in math mode. It'll be easier. Yeah. Go. Yeah. Insert an equation. And say P of A given B. Yeah. P of A. P of B given A times P of A. And then, all right. So, no. Before that, before the P of B given A, type /frac FRA. No, backslash frac, and space. No, FRAC. It's fraction. Yeah. Okay. Now take that P of B given A and put it on top. Yeah. There you go.
I'm actually more familiar with MathJax. I think
it's just like tech. Yeah, it is
I'm a little bit awkward using this editor, but okay.
Right, but you've used LaTeX or tech?
Yeah.
Yeah, it's exactly the same. That's what you were saying, right?
Yeah.
Right. So here you can say, and the denominator you're just going to say P of B. Okay. Right. This is called Bayes' rule. It's conditional probability. Yeah. Now, what is so if you have many different, all right, so P of B, if you have many different authors you want to consider, the denominator is going to be constant in the argmax. What I'm trying to say is that in the argmax you have, in the equation you have up there, in the argmax, that denominator P of B has been ignored. Yes? We're only trying to maximize the product here. We're ignoring the division by the denominator.
Yeah.
And the reason is that denominator is going to be the same number for all of the authors.
Okay.
No, you shouldn't say okay. Right? So the denominator is the same number because what is the denominator? So in fact, what did I say? So no, it's not. Or BAYE, yes. BAY. No. Here BAYE. BAYE. He's a guy. Okay. Apostrophe s. BAYE. That's his name, right? Bayes' rule. Apostrophe s. Bayes' rule.
I don't really know how to type this.
No, apostrophe is shift double quote. No, double quote. No, single quote. Base rule. Yeah. So that's base rule. So suppose we want to apply this rule up there. So we want to know what is a probability. So there in our first equation, you know what we can do? Where you say argmax, bring that argmax to the next line, and then we'll label that equation as equation 1 or something like that. Yeah, bring it to the next line and say put 1 in square bracket, one within parentheses at some n. Yeah, there we go. Yeah, like, and space after that too, so that right now. So equation 1, in equation 1, so you can say after go to the end of the document now. You can say in equation 1 we ignore the denominator because the probability of the text according to any author. So the denominator is going to be the denominator is P of t, isn't it? The denominator is P of t, which is what we're ignoring. Yes.
Yeah.
So what is P of t? P of t is nothing but you can say denominator P of t, right? P of text or P of text. Yeah. All right. Good. Right? Because it is because the probability of the text according to each author is exactly the same, and is equal to and is equal to, right? And is given by. And on the next line you can start another equation, and you can say P of t equals right now you say backslash sigma. I think it's backslash, maybe it's sigma space. No, backslash sum. Space sum, right? And here you're going to say you can basically say A belongs to author. You had that before. A belongs A instead of all authors. Yeah. All right. So and then you're going to say up. There you go. Yeah. No, where you have not up. You can space. And you're going to say P of A. Hang on. Yeah, that's right. And P of t given A times P of A. P of t given A times P of A.
P of t given A.
Yeah, well, whatever you have up
P of A
times P of A, right? So essentially what we're doing is we're normalizing the sum, and that is going to be the same regardless of which author you're calculating. And therefore what we do is, we don't want to calculate the whole quantity because the denominator is going to be the same. What we're interested in is only the maximum, so that since the same number is going to divide everything, we'll just ignore the denominator and we'll only try to maximize that. And that is what the word argmax means. So the word argmax in that equation means what is the argument A that maximizes this quantity on the right? Okay. Does that make sense?
Yeah.
Right. So that is why we ignore the denominator, and that is what we're trying to maximize there. Does it make sense now?
Yeah.
Now go to the end. Go and you can enter and say that is why we. Yeah, so you have because the probability of the text, you've got that already. Okay, right. So now you can get rid of that is why we, right? So now what we need to do is we make one more assumption here. Saying that any author is equally likely before a priori, right? Any author has an equal prior likelihood, meaning that if I give you a random piece of text, and Shakespeare has written like 5 million plays, and Charles Dickens has written only 10 plays. Yeah. And I give you a random play and say, who wrote it? You'll say, yeah, Shakespeare wrote it, because the chances are very high that it's Shakespeare play. He's written lots of plays, Charles Dickens. Yeah, exactly, right? Yeah. Right. So now that is the truth. That is what is out there. However, we're going to make another simplifying assumption. See how many simplifying assumptions we're making here in order to get to some reasonable answer. Each of those simplifying assumptions are places where you can come back and inject more evidence to say, I'm not going to make that assumption. And that each one of those will start improving your model later on.
Yeah, it's
Does that make sense?
like doing science.
Yeah, exactly, right?
Okay.
So so that means that we can rewrite our equation 1. So we can rewrite so we can rewrite equation 1. So we can simplify equation 1 to now copy that equation and put it, yeah, equation 1. No, 1 within parentheses. You got to say,
Yeah.
not, yeah, 1 within parentheses, right? So you
Copy
copy the
it.
whole thing. Yeah, put it there. And yeah, oh, it actually put 2. Did you put 2 or
Oh,
it?
yeah. No, it's because I put 1 here, so it
Oh,
increments.
I'm saying I've never seen that happen because it's not a clear bulleted list, right? It's not a bulleted list, and
It's
you know you
not.
got paragraphs intervening, but still Google somehow figured out that this is
Yeah.
another equation and it needs to be. That's very cool.
It's getting
I didn't
started.
see that happen before. That's very nice, very nice. Okay, now you can get rid of P of A. You can get rid of P of A.
All right.
Right? So now this simplifies our model. You can star also can go, right? Star also. So all we're doing here is saying, you know, the author that we are after is basically the author that maximizes the probability of the text given that author.
Okay.
Right? So you see, after a lot of unrealistic simplifications, right? So you can put that on the next line too, right? After a lot of after a lot of unrealistic simplifications, we arrived at equation 2. This is good enough to get a proof of concept, after which we can go back and make, you know, get rid of the unrealistic assumptions one by one, right? Yeah. We derive equation 2. And so later on we can,
Proof of
so
concept.
now what is the P of text given A? So here again, we're going to say, we're going to make one more simplifying assumption here. The probability of a text, what is a text? The text is basically, it's going to be clean text. Yes, it's coming through after your clean up script. That's the text, isn't it?
Yeah.
So your text is basically going to be a stream of sentences, one sentence per line, and each sentence all lowercase, words tokenized. It's called tokenization. Words are tokenized, right? So we just basically want to calculate. So the text is simply the text is simply a stream of tokens. A text is simply a stream of tokens, right? And since we are calculating unigram probabilities, right? Unigram meaning since we're calculating unigram probabilities, and within parentheses you can say unigram means the probability of a word without being conditioned on its predecessors. Without being conditioned, yeah, the probability of a word without being conditioned on its history. Without is one word, yeah. Without being conditioned, without being conditioned on its history. Predecessors. Yeah. So we can simplify things and say that the probability of a sentence W1 ... W1 is simply, right? So the probability of a sentence, P of S, right? P of S is given by P of S. No, a probability of a sentence S. Probability of a sentence S equals no, right there. No, you don't need to. S equals W1 space W2 space ... up to WN. Actually, use 1 to N. It'll be easier. You don't have to type that N minus 1 at the end, which is a pain. Yeah, WN. Right? Equals on the next. Oh no, is given by. On the next line. You can say P of S equals, yeah, equation. P of S equals product, right? So slash prod should work. Okay, slash prod. Yay, it works. Okay, great. Can you move your mouse so because it doesn't prod, and you say I equals 1, and on the top you say n, right? And for the parameter for the product you say P of WI. WI given A. right? Oh, and also you need P of S given A too, right? P of S given A.
Times.
No, on the left-hand side of the, on the L value.
Oh, okay.
P of S given
Makes
A.
sense. Makes sense.
Right? That doesn't make sense. So far, everything makes sense. Yes?
Yes.
So the probability of a sentence is nothing but the probability of the words in the sentence. Yeah?
Yeah.
Now, so now we can say what's the probability of the entire corpus, which has many sentences in it.
Mm-hmm.
It is simply the product of the probabilities of all of the individual sentences.
Yeah.
Yeah. So now we can rewrite this equation as saying the P of text equals P of text on the next line, the P of T given A, P of T given A equals product of yeah, the same as before, except instead of WI, say SI. Sentence, the product of each sentence, right? The probability of each sentence, you're going to take the probability of each sentence and multiply them all together. I equals 1 to N, P of SI given A.
P of S given
SI
I.
given A. Yeah, so that's what we want to calculate. So the probability of the text given the author is this. This is what we calculate.
So this is just a process of breaking it down from text into a sentence and then to words.
Exactly.
And then we make a product of all of them, and then get a final probability.
That is a final probability. You see how the math model is actually very simple. Yes.
Yeah.
So all we need is just getting. That's what we need to calculate. And how do we calculate that? So in order to get the probability of SI given A, we need the probability of the individual words. Yeah, because the individual word probabilities are multiplied to get the sentence probability. How do we get the individual probabilities of the individual words? The probabilities of the individual words are simply their relative frequencies. Okay, so we're just going to say that the probability of a word is the number of times a word has occurred divided by the total number of times any word has occurred.
Yeah.
So that's a relative frequency.
Yeah.
Okay, so so you can put a statement there. You can write a statement. Now we will assume that we make another assumption. Yeah, we will assume. We assume. Yeah, we would assume that P of WI given A.
We want to put.
No, you don't have. You can actually do even without math mode. Your underscore will work. No, W and W. No. You have to do shift type W, and then say shift comma. I think shift comma. Shift comma. Oh, shift comma doesn't work. Control comma maybe.
Oh, control comma.
What did you do? What did you do? How did you get that?
Control comma.
Oh, control comma. All right.
Yeah,
control comma. WI, and then hit control comma one more time. Otherwise, it won't do. One more time. All right. WI given P of WI given A, maybe given A equals. Oh, is approximated by the relative frequency of word I for the given author.
Approximated by the
relative frequency. Relative frequency
of word I given the author A.
Exactly. All right. So, and then we can also spell it out in mathematical words just to make it very clear in case you forget. I don't think you'll forget. So on the next line, you can say, so P of WI given A, P of WI given A equals A equals total count of word I in by author A. Totally. Slash frac. You need slash frac. Yeah, and numerator should be a count of word I in author or count of word I in author A's corpus divided by CORPUS, no OUS, yeah, no O before the U, corpus, and divided by count of all words in author A's corpus. Yeah, that's again, it is not the true probability, but we're just going to assume, and it does a reasonably good job. Okay, so this is our unigram model. There's one more step we need to cover before you can actually go ahead and implement it, and I'll go over that. It's called the smoothing. and I'll tell you what the smoothing problem is. You know, the stuff that we're talking about today is actually this is machine learning 101. Yeah, and we do this in graduate level classes. And I don't know if you've already done this in other classes before, but you can see how this is all very simple, right?
Yeah.
Even when in graduate level, it's all very simple. It's all built on what we've already done. So that's why. Right, so all right. So here, where I was going with that was the smoothing that I'm going to describe is slightly more, very, very slightly more. I shouldn't say complex, more involved than this, but again, it is also very simple. Okay. All right. So this is what we need to do. So we need to calculate. This is how you calculate the probability of a probability of. So now at this point, do you know how to calculate P of t given A?
I have to check it. I can.
No. You don't have to check. Right here, probability of t given A is nothing but the product of the probabilities of P of Si given A.
P of Si.
Probability of the probability of the entire text, according to Oliver, the probability that the entire text was written by Oliver, is basically the product of the probability of the first sentence was written by Oliver, times the probability of the second sentence, right?
Exactly.
So you want to multiply all the probabilities, right? And so how do you get the probability of each sentence? It's again the probability of each word multiplied.
Exactly.
Right. Okay. So that's what we do. Get that argmax thing back again one more time. I want to show one more thing before we.
Argmax.
Yeah, argmax. Is that the one we
copy
want?
paste
Okay, yeah, put it there. Yeah, put it there. Oh no, we want the one with the product. We want the one with the product. Not that one. There. I think P of t given A. This one. The P of t given. Yeah, take that. Yeah, put it there. Right now, you know that if I want to maximize a function f of x, find the x for which f of x is maximum. To actually find it, you differentiate it and so on and so forth. That's not where I'm going, right?
Okay.
So, but I'm saying that maximizing f of x is exactly the same as maximizing log f of x. Now, that is are you convinced that is true? Because it's a very important thing and it's very simple. Maximizing a function is the same as maximizing the log of the function because they're both monotonically increasing. If this function increases, the log of the function also increases. So if you're going to maximize this, you can also maximize that. Yes?
The domain of log function is always greater or equal to 0, right? Or greater than or equal to 0.
Yes. It's the domain is always not the range.
Okay.
The domain is greater than or equal to 0. That is fine. But then that's not where we're going. What I'm saying is that the value of x for which f of x is maximum is also the same value for which log f of x is maximum. Yeah. Yes?
Yeah.
So if I want to maximize f of x, if I want to find the x for which f of x is maximum, I can also equivalently, right? No change. I can also find the x for which log f of x is maximum. Yes or no?
Yes. I see what you're doing here. You're gonna make these multiplications into additions.
Yes. Okay, very good. Fantastic. Okay. Now it has two good effects for us. Okay. Two beautiful side effects for us. Number one is that if we're going to stay in probability space, okay, regular space, you'll see that these probabilities are really, really tiny. You know, look at Shakespeare's words, right? Or each word, you know, a word occurs 10 times, but Shakespeare wrote 5,000, let's say 5 million words. Yeah. So the probability of that one word is very low. It's like, 10 to the minus 5, 10 to the minus 6 or something like that. Yes.
Yeah.
Each word has low probability. Now imagine what will happen if I take this sentence has 15,000, 20 words in it, and I want to find the probability of the sentence. It's a product of all the probabilities of 15 words, and each word the probability is like 10 to the minus 5. So when I multiply all those probabilities, the resultant probability of the sentence will be so low, isn't it? Because 10 to the minus 5 times 10 to the minus 5, 10 to the minus 7, 10 to the minus 700 even, right?
Yeah.
So the resultant probability will be so low that you're going to, if you're storing it in a float or a double, even then you'll have underflow and you'll lose a lot of information.
Yeah.
Right? Therefore, but if you go to log space, that problem has been solved, because now the log of a very small number is now, if I take 10, what's the log of 10 to the negative 5,000? This is my negative 5,000.
Yeah.
Right? So when you go to log space, all of a sudden that the thing has been squished down. So these extremely small numbers have disappeared now. Now we're in log space. So that's one thing. And the other thing is that we don't have to mess around with multiplication anymore, which is a real pain. And you just do addition. So it has solved two problems for us with one change. Okay, so on the next line, we can say equivalently, right? We can also, oh, where's that argmax gone? Oh, I see. Argmax.
Oh, we need argmax.
Yeah, okay. Maybe, but I think you understand this because you were saying all the right things. We wouldn't have to waste time talking about this, but you can write this out later on your own. What we're trying to do is in argmax, instead of argmax the product of the probabilities, we're going to argmax the sum of the log probabilities. That's all. Yeah. Instead of doing argmax of the product of the probabilities, we can argmax the sum of the log probabilities and get the same effect. Log probs, yeah. So far, does it make sense?
Yes.
Great. Okay. Now, all that remains now is that in your hash table, right? When you read in all the words, you're going to calculate the probability and also the log probability, and the log probability is what you're going to store. So the key is the word, and the log probability is the value. So when you look up the words, you're getting a log prob, which you just add, keep on adding. So it'll simplify your life a great deal. Yeah. So hash table stores log probabilities for each word. Okay.
So
all right.
I do it sentence by sentence, right?
Yes. No, you do it word by word. Eventually you'll do it word by word.
Yeah.
Right? Because after you,
based on this.
Yes, exactly.
Okay.
And that word should have all of the words, including tokens. Basically, not words, tokens. Even the slash s and the s tag, they're also considered words.
Yeah.
So right, so they're all tokens, and so in fact.
Yeah. So right now these formulas are all product, and then if we just apply log to each term, it's gonna be the sum instead of product.
Okay. Yes. All right.
And that's what we're doing here. Okay.
Yeah. So far it's okay, right?
Yeah.
So let's see how we're doing on time, because you got a class at 10 a.m.
Yeah.
Oh God.
I probably have like 10 more minutes at most.
10 more minutes. Okay. So I'll just describe what we need to do, and then you can think about it. And then when you schedule your next meeting, we can talk more about what we need to do. But you'll probably make a lot of headway before then too. Right. Okay. So I want to talk about an important thing here, which is called smoothing. Okay. Say smoothing in uppercase, because smoothing. Say smoothing in uppercase. Oh yeah, that's fine. Smoothing. Okay. On the next line, you say, so when we're calculating probabilities on the test corpus, when we're calculating probabilities of words on the test corpus, okay, not on the training corpus. The training corpus is, so you got data. Let's say you got 1 million terabytes of data. Yeah. Now, in order to train your model, you're going to split the data. You're going to say, all right, 75% of the million terabytes, right? 75% of it is going to go into my training, where I calculate the probabilities, and the 25% that is not going into the training, that is my held out. Why? In machine learning, you always split the data into a training part and then the held out part. Okay. Why is that important? Because you want to test if your model is good or not. Yes.
Yeah.
You can't test your model by giving it the same data that you used to train it. Then you'll say, yeah, I already saw that data. It is Shakespeare. Yeah. So when you test it, you want to give it something that it's never seen before.
Yeah.
That is why when you take all of Shakespeare, only 75% of the Shakespeare text will go into training your language model. 25% is what is called held out data, which you're going to use to test it.
Yeah.
Right. Now, here is the challenge. What
Mhm.
happens if there is a word in your test data that was never seen in the training data? Never seen, okay? There's a word in the test data that Shakespeare used that it was never seen in the training data. What will happen then?
It's gonna
Held out
generate
is
random.
not held up data, it's held out data, held out.
Held
It's called
out.
held out.
Yeah.
Yeah, right. So what? So now on the next line you say blank line and then say question. Yeah, question. You say question. Yeah, say question. What happens? What happens if there is a word in the test data that has never occurred in the training data? So can you guess before I tell you what will happen?
It's gonna generate random result.
No, it'll be zero, right? Because that word was never seen in the training data. Therefore, the frequency of that word is zero in the training data.
Yeah. So the probability
Therefore, the
is zero.
probability of that word is zero.
Yeah.
Right? But the probability of the sentence is a product of the probability of all of the words.
Yeah.
So, but one of them is zero. Yes?
Mm.
So the entire probability will become zero. Even if one word in the corpus has not been seen before, the entire corpus will evaluate as zero probability.
Yeah.
So we want to avoid that, yes or no?
Yeah, we want to avoid that.
Okay, all right. So that is where we try to do something called smoothing. And smoothing says, but I don't know if you would call it smoothing. Smoothing is more like interpolation. So because smoothing, this is called the unknown token problem, or I don't know what it's called, right? So it's a word that you've never seen before. So what we'll do is that, can you draw, unknown token problem? Yeah, unknown token. Unknown, KNOWN, KN, right? Unknown token problem.
Yeah.
No, unknown, not you got known now.
Oh yeah.
Unknown token problem. So you get a stream of words, and one of the words has never been seen. And the problem only exists if you take that entire probability space. Consider that, probability of 1 is that circle, the area of the circle, that whole circle is 1. Yeah?
Yeah.
Now so that entire circle has now been taken pieces of it and given to each word, okay? So you add up all of the little chunks given to each of the words, you get 1.0. So that's the whole circle.
Yeah.
Now, if you did that, you're saying this whole circle is all of the words. There is no word that's out of the circle at all. So if you see that word, any word that is not in the circle has zero probability. That is dangerous, isn't it?
Yeah.
So we're going to make that very simple assumption here, saying, okay, we will assume that there is no such thing as a completely unknown word. It just means that that word has not been seen by us. That means that if you sum up the probabilities of all of the words that you've seen, it is not 1, it's slightly less than 1.
Okay.
Right? So that means there's a little bit of probability left over for something that you've never seen before.
Yeah.
And it'll be a very small number, obviously.
Is it possible that we run out of that buffer area? Is it possible that we run out of that area if we encounter?
No. Okay. So this is what we're going to do, right? So so we can solve that problem in many different ways. And next time when we meet, I'll talk about some more sophisticated ways of dealing with that. But what we'll do here in this project, initially, the first cut. So say for the first cut of this project, we will use Laplace-1 smoothing. Okay, type this out, and you can Google it too, right? Later on, for the first cut of this project, for the first version of this, the first cut of this project, we will just use Laplace-1 smoothing. It is called Laplace-1 smoothing, or we'll call just use add-1 smoothing. Call it add-1 smoothing. Add-1. Add-1. Yeah. Add-1 smoothing to handle the case for unknown words. Okay. So that means so you can say that means the probability of a word P of Wi, right, is now, right, it's equals, and where did you have that equation there that you counted frequencies and all, kind of count of, further up in the document you had count of all words. You had somewhere you had count of all words. Yeah, there you go. Yeah, right. There you put that there. Put it there. Equals. Yeah, equals. So right on in the numerator, you're basically going to say count of all words plus 1. So you'll never have 0 in the numerator.
Count of all words plus 1.
Yeah, and the denominator, if you want to normalize everything, has got to be count of all words in author A's corpus plus vocabulary size, which is the number of words. Because, well, actually, you know what? Plus 1 smoothing, you add 1 and divide by. How do you smooth this? Gee, because we're in a time crunch, I'm right, count of all words plus 1, and then the denominator has got to be it doesn't normalize if I do it that way. I got to think more about this, but you can Google it. It's very simple. If you Google
what's the
add one,
of this?
if you Google add one, don't do it now. You don't have time, right?
Yeah.
But if you Google it later, you'll see that in just in the first paragraph. It's very easy. Or you don't even have to Google it. You can think about how to solve it yourself. All we're doing is that we're adding 1 to the counts of all of the words. That's all. Adding 1 to the counts of all of the words. Any word that comes in, you're going to add 1 to it before you divide by the denominator.
Okay.
But then you also have to make sure that the denominator is greater than everything. So you got to somehow figure out how this whole space is normalized. I can think about it more, or I can even look up, what I did before. I'm sure there must be. Right? So that's what we need to do. So that is called smoothing. The smoothing is a technique by which we make sure that unknown words also have non-zero probability. Right? Smoothing. You can after the word smoothing, you can say smoothing is a way. This is a way to make sure that unseen words in the training corpus also have non-zero probability.
Corpus also
non-zero probability.
Non-zero probabilities.
Yeah. Okay. All right. So that's what smoothing is. You can Google add 1 smoothing and find out. I'll develop this, because I'm just developing this whole, we're coming up with this framework as during the Zoom meeting. We're not able to. You can find out, okay? Or next time I will tell you what to do.
Okay.
But are you comfortable with that? Are you comfortable with finding out how to do the add 1 smoothing and incorporating that into the model?
Yeah, that's pretty interesting.
Yeah, it's actually super duper interesting, right?
Yeah.
Once you have that, I'll show you how to turn this into the next step will be a bigram model. And also I'll show you better ways of doing smoothing than add 1. So add 1 smoothing is actually one of the inferior smoothing techniques, although it's easy and I shouldn't say inferior. It does the job well most of the time, but it's not the best we know. There's better ways of smoothing. There's one other technique called Witten-Bell smoothing, which is actually, and good Turing smoothing, Kneser-Rennet smoothing. They're all more sophisticated smoothing techniques, which I'll show you later on that we can use. But this is a good start. There's one more thing. Back off. Back off. We'll do back offs when we do bigrams, right? When we do so when we calculate bigram probabilities, that's what's the probability of the word given the previous word? Then there's a higher chance that the word may be unknown following that word. Yes, because previously you took the total frequencies, but if you're taking words that only follow a certain word, maybe there's higher chance that word will be absent. So it's far more important when you go to bigram and higher order models that you have proper smoothing and interpolation in place. So the usual way to do that smoothing there is to say, I'll take the bigram probability. If the bigram probability is 0 because the word never occurred in this context, then I'm going to back off and use a unigram probability.
Oh, okay.
Right? And so again, for bigram, the unit circle for the probability of 1 for bigram, again, you're going to carve out. You're going to take a chunk of that out and say, well, you know what? I'm going to take the bigram probabilities and all of the bigram probabilities added up will only add up to 0.75. 0.25 is the back off probability of the unigrams. So anything that's not seen in the bigrams, you'll go to unigram and say, put that in with a 0.25 weight.
Yeah.
Anything that's not seen in the unigram, you'll go to the add 1 smoothing and put it in with even lower weight. So now you can get a system by which any word will have a non-zero probability.
Yeah.
right? And now you can calculate the probability of the words for a given author. You can do the multiplications, and you can calculate the probability of the entire text, and you'll be able to come up with a quantitative measure saying this is the most likely author, because that's the one that has the argmax.
Yeah.
Does it all make sense?
Yes.
Right. Okay. So anyway, since this was the first meeting, we just did an overall bird's eye view of saying, well, this is how everything is, this is how pieces fit together. Now, when we start meeting from the next time onwards, we'll be starting to look at the individual parts and saying, oh, this is the implementation, we can tweak things here and so on and so forth, and we'll start moving in the right direction. Okay. All I needed to share today was basically just give a rough idea of the big picture. And I hope that has been conveyed, right? You have an idea of the big picture, where we're shooting for, right?
Yes. Today? Yeah. Great. Exactly.
Okay. All right. So that's really all that's needed, because I think, based on what you've done in class and your discussions and all, I'm pretty confident that even without my input, you can actually take this a great distance, right? So you'd be able to get to a good place before we meet the next time. It could be any time, right? Even tomorrow, next week, whenever it is, when you're ready. Okay. Anytime you want, because this quarter I'm not teaching, so I'm free most of the time. Other than other work, I can reschedule. Just let me know, and you say, hey, Anand, I've done this. I've got some intermediate results. You want to take a look? Or I'm stuck here. Can we take a look, and can we solve this problem together? All of that is perfectly fine. We can get together and work on this again. Okay. But hopefully you have enough here. And since you're working on Unix and you have Python and your editor and so on, do the cleanup script and then do this. Get some initial version. You don't have to do a complete app. You can just run everything by hand. Right. So piece of text, you can say, this text, who wrote it? You can just type 5 commands. Calculate probability by Shakespeare, calculate probability by Dickens, and look at the 5 numbers. Hey, all right, according to the system, you're writing like Mark Twain, something like that. Yeah. You can do that. Eventually, later on, you can put everything into a single system with the user interface and everything.
So I think now we can just do the modeling of the probability of each author's
each other's sets. And the thing that you may need to do is that after you calculate the log probabilities, you need to store them in a file. Yeah. So store them in a file saying, Twain dot lm, call it lm for a language model. Okay. Right. And in that file, all you'll have is word, floating point number, word, number, word, number, word, number, word, number, all of the words. That's all.
Okay.
And you'll have one of those for each of the authors. And then when it comes to classification time, you're going to, your C++ program is going to read all of those files and essentially load them directly into a hash. Read the file and it has a key value, load them into a hash.
Yeah.
So you have like 5 hashes or 10 hashes or 1 hash for each author.
Yeah.
And then then a text piece comes in and says, who wrote this? And then you apply the exact same cleanup procedure to the text that's coming in. Break it down into components, individual words. Each word, you look up the hash table for each of the authors and find the probabilities. So you can calculate the probability of the text, this author, probability of the text for this author, and so on. You can print out all the probabilities.
Wow, that's super cool.
Yeah, it's really cool. It's really cool. It'll be fun. Once you have this working, maybe you can even demo this in the STEM Center, or you can present. I think at some point there'll be something called an RSL, right? Research and Service Leadership Symposium. I think they do that at Foothill. I know you posted something from the business department, business and social studies department. Yes.
Yeah.
Right. I think there are people in that department who run the RSL. Right. It happens in May or sometime in May or June. And that the RSL is where students from all over the campus will present projects related to research or something they've done.
Yeah.
And there's a prize also. And so if you get this done, you can also present this. And in the conference, in the RSL conference, you can ask people, right? Hey, volunteer, come and type something in. My system will tell you who you're typing like, right? It'll be a lot of fun. Lots of people will come and try it out. And I think it'll be really cool. And then at the end, you can say, well, at the end of your presentation, you can say, well, now that I've classified all the text, I'm going to try and generate text like Mark Twain. Okay. So you say, all right, here's a story written by Mark Twain, but was not written by Mark Twain. You press a button and you get something, right? In Mark Twain style, but it wasn't actually written by Mark Twain. You can try and do that too. And say that is the crowning glory of your presentation. Say, oh, that's fine, right? So you end with a bang like that. Okay, thank you very
All right.
much. I think you have enough time to get to your next class now.
Yeah.
All right. So I think it'll be fun, Oliver, and hopefully you'll get this project interesting, and talk about this, and more people, you recruit more people from our class, right, into
Yeah.
this eventually, and so that you have a core group of people working on this, and different people can do different things. By the end of the quarter, maybe you'll have something really, really sophisticated too.
Yeah. That'd be pretty interesting.
Yeah, awesome, fantastic. I'm happy, right? I'm actually very happy that this quarter, we're starting all these things sooner. We don't have to wait until week 8, week 6, and so on and so forth, which means we have more time.
Yeah.
Right. All right, wonderful. All
All
right, best
right.
of luck. Talk to
Yeah.
you later.
See
Bye.
you. Bye.